So my name is Sinan Ozdemir. I am so happy to be here. I am head of AI education at Fireworks as of only a couple of weeks ago. But for those who may be familiar with my work in the past, I'll give you the long story short. I built one of the so I'm a former mathematician. I got my degrees in theoretical mathematics from the Johns Hopkins University, where I also taught for a number of years. I actually built one of YC's, as far as I'm aware, YC's first generative AI company in 2015, where we were building agentic generative models. Yes, before the transformer even existed, those existed. We even patented the agent in 2019. Since then, I've also authored my own set of books. I know, at least a few people have mentioned them. They're available. You can find it. I have a pretty unique name, so they're pretty easy to find. I won't. But that's not why you're here. You're here because you want to hear about how you can optimize your model inference. And I think I want to take a little bit of a different approach today and to a lot of the other wonderful presenters. And there's no question that on the serving side with better kernels, smarter caching, faster hardware, better networking systems, there without a doubt, these are crucial components of your inference side of your LLM usage, your AI usage. But what do we do with that speed is what I want to focus on today, because a lot of what I do at Fireworks and a lot of what I've been teaching over the last decade and a half at this point is the techniques behind the AIs. What techniques do we have in our tool belt to make our inference more optimized, whether that is for quality, for cost, or for latency. So I'm going to be focusing more on the model side of optimization today, because again, you've heard, over and over again, we want to make sure that we're getting fast throughput, lower latencies on the server, on the serving side. But what do we do with the speed of those models once they are ready for us? So I'm going to talk about three different applications. And I write in order of effort, but that's a little subjective, and I think that's people will find that they'll grasp onto one of these different categories a little bit more, however you want. So, but we're going to go through three different levers today, and these aren't the only levers at your disposal, of course, but they're the levers I had time to talk about in my 30 minutes with you all. So, we're going to talk about capping, distilling, and routing. And we're going to start with a pretty kind of straightforward one, in my humble opinion, which is capping. And the idea behind capping is that these days it's almost harder to find a model that is not a reasoning model. And for those you might remember a few years ago, it was the opposite. Most models were non-reasoning, non-thinking, and then there was this kind of period in which we had a few LLMs that had some reasoning. You could turn it off, you could turn it on. It was low, it was medium, it was high. And today, virtually every LLM that comes out of a frontier lab, open source or closed, has some kind of reasoning enabled. And I think it's kind of an expectation. Now, here's where I want to make a kind of a big claim. And one of the first things I noticed when reasoning models came out was we had already been implementing reasoning as prompt engineers, context engineers, as LLM engineers. We had this concept of a chain of thought prompt, meaning you ask the AI to reason through what it is before actually answering the task. So the concept of having the AI think out loud before answering the question, that's not necessarily the new thing. Now they're just built into the model. That's what's new. But here's the kicker. Most models will have some kind of a range between low, medium, high, or maybe you'll see like a max and X max, there's different levels of thinking. And some models will give you the benefit of turning reasoning off. Not all models do that, but some do. Kimi is one of those models that will actually let you turn the reasoning off entirely. Now, I know everyone's, watching virtually, but raise your hand if you are someone who is very likely to say, well, if you're going to let me reason more reasoning means better results. And if my serving side is optimized, then I should be able to see those fast reasoning tokens come in and see my better results even faster. But here's the problem with that. Even though it's only one line to change your reasoning effort from low to high, high to medium, you actually are potentially staring down some not so great results. So, to put this in perspective, I'll give you an example. Many of you are probably familiar with this benchmark called tau squared, the tau squared benchmark. Basically, it's an agentic benchmark in which the AI is acting as a customer service agent, talking to another simulated user who is also an AI. And the idea is that you are judging the customer support agent, the LLM agent, in its ability to either help or refuse to help in some situations what the human is asking for. It's a pretty common benchmark. You'll see it actually reported on a lot of the frontier AIs these days. So I chose it as an example. So what I did was I took a model on the Fireworks serverless system, Kimi in this case, and all I did was I ran the Kimi model through the benchmark at varying reasoning efforts. So in Kimi's case, I did none, so no reasoning whatsoever, low, medium, and high. Everything else stand exactly the same. Same prompt, same benchmark subset, same everything. But here's the kicker. When I ran this 3 times for each question, so we call that pass at 3, the results were pretty, I mean, in my, when I've done this in the past, not surprising to me, but can be surprising to a lot of people. The non-reasoning turned out to be just as good, just statistically speaking, within a single standard error as low, medium, and high. So even when you turned up reasoning all the way, the LLM did not actually get any better at that benchmark, which is counterintuitive. You would assume, well, reasoning should make it smarter at doing the task in front of it. But that's just not always true. In fact, if you look closely at a lot of benchmark scores, you'll often find that the difference between medium, low, and high is a lot smaller than you might think. But if you look on the right, what you really will notice as you turn up the reasoning levels are the amount of tokens being shoved out of that model, and therefore the latency, the speed that you're experiencing from that system really drastically changes. So from a P50, a median latency of roughly 40 seconds to solve a task, it would go to 60 seconds median when the reasoning is turned up all the way. And again, you're not getting any accuracy quality bonus here. So with all that speed, you're still not getting any results. Now, again, this might seem like a simple experiment, because it is. That's kind of the point of what I want to be getting across today, which is what we do with the speed of these models is it enables us to run these kinds of experiments a lot faster than we could even a few years ago. So given that, there was no reliable gain, frankly, in this case. Now, I'm not saying reasoning never will help. I'm saying in this particular case, as it might be for your particular case, reasoning might not help. There's actually another case study I do in my, I think it's my most recent agents book that's on that I published a couple of months ago. The same thing I could find with computer use, vision models. Vision models did not benefit from having more reasoning outside of maybe 1 or 2 percentage points in their ability to use a browser. But it sure did double the latency of actually running that task in some cases. So when you have this speed in front of you, the first thing I want people's intentions to be with that speed is experiment. Try different things as quickly as possible to see what works best for you. So let's move on then to the more harder aspects of what you can do with that speed. And this is going to sound very similar to some of the other talks today, because now we're getting into some more fine tuning, some training aspects of what you can do with that speed. So if you've never heard of distillation, or you want a quick refresh on distillation, the concept of distillation can actually take on many different forms. People can mean different things when they say distillation, even more than these 2 things on the screen here. But the general idea of a distillation task is to transfer the knowledge from a usually much bigger frontier LLM into a much smaller LLM who can do that task, and usually only that task, but just as well as the frontier AI and at a fraction of the speed and cost. Now, from there, you can get more specific. You can talk about distribution distillation, data distillation, on policy, self distillations. There's a lot of different types of distillations out there. Fireworks supports a good amount of those types of distillations, namely distribution, distillate data, and in some cases that on policy distribution. Now, what's most common is the data distillation. This is what most people think of when they hear the word distillation. The idea is that you have an AI, a bigger frontier model, generate some output oops, generate some output, and then you use that output, that completion, as training data, supervised training data, to train a student, a smaller model, not necessarily the same family or same tokenizer, which is what makes data distillation very attractive. The idea is, for some kinds of distillation, not that it requires it, it gets much harder to do when you have different model families and different tokenizers. With a data distillation, you have the big model answer a question, you grade it, hopefully that it's correct, then you use that as data to train a smaller model to say, do it like this, follow these instructions, do the conversation as I'm showing you here. So this is data distillation, and arguably, it's the simplest kind of distillation out there on the market. And again, it's what most people think of when they think of distillation. So how do the numbers work out? I mean, as you might suspect, the numbers work out quite well. And just kind of using some, picking a model off the shelf on Fireworks and giving you the prices here. If you were using a model like Kimi K2.5 with the price and cost and everything that you see here, you would, in theory, be saving thousands of dollars a day simply by distilling a certain task into a smaller model. And we have a lot of case studies in of our customers who do work like this, and I link to some of them in the final one pager. That there's a QR code at the end. But this kind of distillation again is really enabled by the speed of the serving side. So everything that people have been talking about today, and better KV caching, better kernels, all of that is for something, and it's not just for generating completions and agent rollouts. But this is also what enables Fireworks to be one of the fastest training solutions on the planet as well. Because we serve models so fast, we can also train them a lot faster as well, and a lot cheaper in most cases. So the conversation around training models is becoming an easier one to have. And I can say that confidently, having had these conversations for 15 years with people, it's never been easier to bring up the concept of fine tuning a model than it is today. And that for me makes me very happy. And that's why I love, being a part of this world and being a part of this ecosystem. Because you don't even need to use Fireworks to get a lot of these benefits. You can run a distillation completely on your own local hardware using open source frameworks and infrastructures, and you will get very similar results than if you do it on some inference provider like Fireworks. Of course, we just want to make it easier for you with bigger models, but it's not like there is a proprietary type of distillation that some companies employ. These are the same kinds of techniques that are simply enabled by better, faster serving architectures. So again, I can show you case studies. I can let you read them for yourself. But the idea of distilling tasks from a large model into a small model is often not only does it work, but it's also usually part of a multi-stage process. So at Fireworks, we often call this a recipe. The idea of using multiple techniques in a sequence so that you can run one technique like supervised fine tuning and then potentially a reinforcement learning after the fact. So you can distill as stage one and then take that distilled model and even imbue even more behavior that you want through a reinforcement learning loop. So distillation is becoming a more common use case for people as they realize we're just using, we're driving this Ferrari to the grocery store, and maybe we can train a smaller car just to do that instead. So when you start to hit these scale problems of we're running basically the same task over and over and over again on this frontier model, it might be time to have that discussion of how do you take that task and teach it to a smaller LLM that you have at your disposal. And that's going to bring me to our last technique here, which is routing. And I know this has come up a few times today, so there might be a little bit of a refresher here. But routing, the concept of routing, picking the right model for the right task is much easier said than done. But I would like to present to you an extremely simplified version of this routing flywheel that has absolutely no human in the loop, but can still show results and something you can get started with literally today. And to show the example, what I did was I took a benchmark called Bird. And if you've never heard of Bird, I don't blame you. It is a text to SQL benchmark. Basically, it's a 33 gigabyte database benchmark with 12,000 plus questions across 95 different databases. And the task is relatively simple. Here's the schema. Here's the question I have. Write me SQL that will answer the question. And surprisingly, you might be surprised to hear this, there's still room at the top of the leaderboard for this benchmark for even the frontier model. So I like to pick this benchmark because it sounds very easy once you hear what it is, but it's actually quite difficult for even some of the frontier models out there. And what's also nice about it is that there's a relatively objective scoring, meaning there is a right answer. I asked a question. I know the answer is in the data. I know what the answer is. There might be some wiggle room in how the model writes the SQL query, but generally is very objectively scored. And more importantly, as you'll see in the next slide, the questions themselves are embeddable, meaning you can take the short form questions of what is being asked and run it through an embedding model for the purposes of adding them to a vector store library. So here's the flywheel that I constructed in the visual format, and let's walk through it left to right. When a question comes in, first thing is we embed that question. Fireworks has embedding models hosted. So for this case, Qwen3, 8 billion embedding model. We then run it through our library, which may be empty, but let's assume it's either empty or not. We find if there is a similar question that has been asked in the past, and we use the embedding similarity as a proxy for that similarity. If the similarity reaches some threshold, like 0.6, there is a question in the database, in the library, that similarly matches the one that's incoming. We route it to the small model. That small model will then attempt to answer that question, and it never goes to a frontier model in the first place. But if nothing matches that question in the library, it goes to the escalate, meaning now we're going to ask both models to answer this question. The user will see the answer from the frontier AI, kind of assuming that the frontier AI is just better at this task. But while that's happening, the small model also takes a crack at it. And this is where you can improve on this flywheel quite frankly, because there is no human in the loop. If the small and the big model agree with each other, that answer, or that question rather, is added to the library because the small model agreed with the big model. That for me is enough to add it to the library so that if a similar question comes in, we're going to send it to that small model instead of the big one. Now, in a real life situation, ideally, you double check the small model's work before adding it to the library. Some human in the loop should be able to check, or some panel of LLM judges, however you'd like to handle that. But in this case, all I did was say, if the big and the small model agree, that's enough for me, add it to the library. So I simulate this over time, and I find a few very interesting things. So if you are looking at cost per query in $, because we're talking about a query is going to be very few tokens compared to what Frontier Labs will charge you, but the cost differential is pretty obvious on the left here. It is 4 times cheaper to use the flywheel versus always using a frontier model. It is almost 3 times faster, two and a half, a 58% reduction in latency, and the accuracy actually was slightly better, actually, by using the flywheel than always asking the frontier model, which, yes, does imply that sometimes the small model actually got something right where the big model didn't. So that can happen. Don't get me wrong. So the flywheel actually ended up being just as good, slightly better than always asking the frontier model. So if you look at it on a graph like this, on a kind of a Pareto graph like this, we have cost on the x-axis and accuracy on the y-axis. You can see a pretty clear story. I'm not claiming this flywheel alone gets you to Opus in sonnet level performance. It's not too far off, don't get me wrong, but you can see how it's on par with the frontier open model that I used, DeepSeek, at a much cheaper price. And it is still better than always asking the small model, the Quen 9 billion. So again, with speed, we have now this concept of, well, I have to ask the models twice if if the similarity is under 0.6. I do have to ask both of these models, and I have to very quickly add it to the library before the next question comes in. So with that speed, we can start to enable these kinds of experiments, which even further optimize your quality, speed, and latency. So none of this was a better kernel, a better GPU, more money being thrown at the serving side. I'm simply using the speed already granted to me to run these kinds of rapid experiments. Another interesting part, by the way, that I wanted to add was, and people usually see this and they think, they get scared away at first, but the idea of a flywheel is that it does have to warm up a little. So in the beginning, there's nothing in the library. So everything keeps getting escalated to the frontier model, which means your costs will start off pretty high. Relatively, you're looking at relatively here. But as the library gets filled with examples that the smaller model is now more confident in tackling and handling, we see that the accuracy, which starts off very, very good because the frontier model is handling most things, settles to that roughly 41% accuracy at answering the question, as does cost and escalation rate. So you start to build this kind of mental model of how often does it actually escalate. And for the numbers here, if it was never escalated versus 15% and 100% escalation, we see all the way, these are pretty big price differentials in more than 4 times cheaper using our flywheel versus always using that frontier model. And again, this was just 2 models off the shelf, DeepSeek V4 and Quen 9 billion. I personally tried about 5 different model combos before settling on this flywheel, but that took me about an hour. Once I had the workflow ready and I had the data set to simulate through, it only took me about an hour to try 5 different combinations and settle on this one. And this was just for this talk. If this was my job, if my job was to be better at text to SQL, I only need a couple of days to run through virtually every model combo on the Fireworks catalog, and I'll get the best possible option I can get from that one catalog alone. So again, faster serving enables faster experimentation, which for me is how you win at the end of the day. Your techniques, how clever you are in how you use the speed of those models, that's what's really going to let you win in the long term. So how you use your models. Copying reasoning is just one example of experimenting with inference parameters. A lot of people will experiment with temperature or top K, top P. Reasoning effort should be another lever that you experiment with, just like any other inference parameter at your disposal. But if that's not getting you the results that you need, which again, capping is not meant to win on quality, it's meant to save you on cost and latency when the quality was already there to begin with. But if you do need to potentially increase quality maybe you'll need a routing situation in which your routing might actually give you better results than simply asking one model all the time. Or distillation, another part of a potentially 2, 3 step process in which you train a smaller model to act like and be as good as a big model at a certain task. So, with that said, I'll say thank you all, of course, for sticking around and making it through the day. And if you did stick around, and I do have a gift for you for sticking around the whole day, at this QR code, you'll find our one pager, basically about this talk. And the first 50 people who get to the one pager, there is a $50 credit to Fireworks if you do actually want to try some of these experiments. And if you do get these credits and build something, please find me on Twitter and LinkedIn. I promise you it's not hard to find me. I have a very unique name, and show me what you've built. I would genuinely love to see what you are building with these models. And more importantly, I would love to see how you experiment with these models on our catalog, not just how you use them, but what experiments did you try to get to where you are. So I'll stop there and happy to take a question or two. But thank you all so much. And I hope you have a wonderful rest of the day.
And that was a lot of good stuff, lots of good tips there. I very much agree with you in some of those suggestions. Because a lot of time people just, by default, just hitting these API with not paying attention to the level of intelligence that's needed for their particular tasks or use cases. So I have asked the attendees to post questions, but while that is showing up, I have a few questions for you.
Please.
You talk about distillation, right?
Mm-hmm.
Definitely, one option to go with.
Sure.
My question is about doing distillation is at least for me, it's not easy. So do you think is this very accessible to AI engineers at the moment, or still very much in the realm of like machine learning engineer?
I think it is rapidly, 10 years ago, it's squarely in the field of machine learning engineers. But one reason that I joined Fireworks was their commitment to making machine learning engineering as simple, quote unquote, as software engineering. And I think a lot of what my new role at Fireworks, is to build that curriculum to convince people to
I
say,
see.
this is now in your hands. This can be in your hands if you want it.
Yeah.
And we are rapidly approaching that threshold where it is as easy it is to code, it is as easy it is to fine tune a model. And that for me is exciting because having built my first YC company 10 years ago on fine tuning, YC would never take my company today because they'll say fine tuning a model, that's nothing. But 10 years ago, it was one of the hardest things you could do, quite
Right.
frankly. So we are getting there. I wouldn't say we're exactly at that, 1-to-1, but I feel like it's never been easier.
Yeah, I agree with that trend with fine tuning. Now it's a lot easier. I mean, Fireworks have done a great job in that space of providing that service. And similar with RL as well, right? It used to be very, very challenging to do RL. Now it's becoming easier, definitely.
Getting easier. I'm not going to tell you it's a
Not
one-click
easy, but
solution, but it's
easier.
getting easier. Yeah. And that's my job, is to walk you through it.
Yeah. All right. That's a question from the attendees, so let me bring it up. As you are doing warm-up, which request?
I will, I assume.
Yeah, go for it.
Yeah, as you're doing warm up, what requests go to the smaller models, and how do you choose that smaller model? So during the warm up, so the basic simplicity of the flywheel is that the decision of when to go to the small model is purely mechanical. If there's something in the library close to the question at hand. Now, that alone, you can disagree with me on, as you should, because as I will always say, everything is an experiment. If you think the better way to do it is to have a grading, a generative grader answer that question for you, I don't disagree. You might need to fine tune that grader to be faster, cheaper, better, but we can have that discussion. To your other question of how do you choose that smaller model, everything is an experiment. The easy,
Yes.
naive answer, which is true, is try them all. If everything is so fast, it shouldn't take that long to get a good sense of which of those models are going to be better. Now, that assumes you have a data set in which you can compare that against. Now, if you don't have that, you can always do what, frankly, most people do, which is find the benchmark scores that best match the task you are trying to do, and then filter it by those benchmarks. Like I said, Bird is not a very widely reported benchmark, but it is a benchmark. So if you want to benchmark a model on the Bird benchmark, you're allowed. No one's stopping you from benchmarking models on a benchmark. In fact, Fireworks even has an open source framework called eval protocol that will help you do that. So by finding benchmarks that closely match the task you're trying to do, simply experiment and find the right models with the right benchmark scores. And if you can't find the benchmark scores, benchmark it yourself.
Awesome. Thank you for that. Thank you, Sinan. Again,
Of
thank you
course.
for your time. Thank you for taking time with your busy schedule and share your expertise and knowledge in this space. Really
So
appreciate
happy
it.
to be here. Thank you all.